Some other information we can get from phase diagrams are things like melting points or boiling points or sublimation points depending on pressure. And so if we want to look at, say, what we call the normal, so I put the water phase diagram here. This looks similar to the benzene one, but is not the same. But the water phase diagram at normal pressure, so we don't have all the crazy different types of ice. So if we want to look at behavior of water under different pressures, a phase diagram gives us that capability. So if we have, say, water at 0.05 atmospheres here, we can sort of go across, write a line across the phase diagram here. And so where we have a coexistence, that is where we're going to have a transition from one phase to the other. And while it's transitioning, you'll have both of those phases in equilibrium. So if it's solid and liquid, that's what we call melting, right? So if we have ice melting at a given pressure, we can read off what that melting point will be from this coexistence curve. Same thing with boiling. That's a transition between liquid and gas. If we have a substance where we're below the triple point here, I'm going to go over to the log graph to make this a little bit clearer to see at very low pressures. If the pressure is below the triple point, we won't ever reach the liquid phase, right? And so we have a transition here that's sublimation, where we go directly from solid to gas. The most notable compound that sublimes at atmospheric pressure is carbon dioxide, because that's behind my face, because carbon dioxide's triple point has a higher pressure than atmospheric pressure. So that means that carbon dioxide never goes to a liquid as it goes from low temperature to high temperature at atmospheric pressure. If you increase the pressure, you can get carbon dioxide to turn into a liquid just like anything else, but just with the specifics of its phase equilibria, CO2 never reaches a liquid state under atmospheric conditions. And so what we can see here is we can look at trends in melting and boiling temperatures as a function of pressure, right? So we can look at the lines along here. So we can see at low pressures, for example, at pretty low pressures, the boiling point of water is below 300 Kelvin. And then as we increase the pressure, we get an increase in the boiling temperature. And so we know at atmospheric pressure, the boiling temperature of water is about 100 degrees Celsius or 373 Kelvin. And so we can see this trend here. The other thing that we can see is that if we instead look at the melting point, the melting temperature, there is very little change here. Now, one notable thing about water is that the slope of this change, now, there is a change, it's hard to see, but there is it has a negative slope on this line here. Most substances have a positive slope. We'll actually look at that later in this chapter as we talk about the thermodynamics of phase equilibria, and we can see why water has that, and it relates to densities. So the fact that liquid water is more dense than solid water is what leads to this negative slope. So we get this behavior. So as we increase the pressure, the melting temperature of water actually decreases. Whereas for the boiling temperature, and this is true for pretty much any substances, it will increase. The boiling temperature will increase. Now, it's not as big of an effect. We can go over many orders of magnitude over here, and there's very little change in that melting temperature. And that's generally true. It has to do with the fact that solids and liquids have very similar molar volumes, very similar densities. Okay. The other thing we can get off from a phase diagram besides these melting and boiling points is also vapor pressures. So if we're looking at the liquid-gas phase boundary here, if we look at a point along here, this will tell us how much gas we would expect to be evaporated. What's the pressure of the gas that's in equilibrium with a liquid. And so, for a given temperature, we can read that off. And when that vapor pressure, when the vapor pressure is equal to the external pressure, or I say when it's equal to atmospheric pressure, that's what we call the normal boiling point. And the boiling point is going to change as a function of pressure, and we can read that off of the phase diagram. So if, for example, you go to Utah, where I did my undergraduate degree, and you boil water there, because its elevation is higher, the pressure is lower, and your water will boil at a lower temperature. That concludes this part of the video talking about phase diagrams. We will look at the last thing we're going to talk about in the next video is this point over here that I've ignored up to this period of time, which is the critical point.